All right, welcome back, everyone. Today, we're going to be going over the project description for the Bluefield State University MIET 312 surface mining class. So we started out here, we've got our project mine map, and I'm going to go over a few things, including the project description itself. So, tasked with designing a combined contour and highwall mining operation in Isaac's Run of central West Virginia. So if we look at the map, we talked about this previously, the reserve is divided into two blocks, a northern reserve and a southern reserve. Okay. The northern reserve has pre-existing surface mining highwall. It also has an outcrop that we'll be ignoring from a surface mining perspective. So we're just assuming that we don't have access to this. We can't get permission for, with a wheelage. We can get a wheelage agreement set up, and so we just can't surface mine this portion. It can also be underground mined. Adverse property boundary is here, meaning we can't mine that. And the pre-existing deep mine is here. And we have outcrop here, and so we'll be mining this area as well, taking these things into account. Right? So, back to the description. Highwall mining will supplement the contour operation, right? Okay, so we're going to have highwall mining, and our slopes and sort of seam thickness for the two reserves, 3 feet in the north, 4 feet in the south, and a surface topography slope, okay, that averages 33% or 18 degrees in the north and 44% or 24 degrees in the south. I previously mentioned that I generally recommended the north as a starting point because there's spoil storage available, that sort of thing. But you can start anywhere you want as long as you, design it that way and all that. I think Isaac's Run represents the best opportunity for a valley fill if you need one. You could also consider side hill fills as well, but we'll calculate if you need one or not. Economic parameters, so we selling the coal for $100 a ton. Mining cost, excluding the overburden, is $40 a ton. And overburden removal cost is $5 a ton. Then you got other numbers for coal density, overburden density, swell factor of 1.25, and then we just assumed 6 day a week, 24 hours operating schedule for both the strip and the highwall miner. Plant recovery, so the highwall miner coal, it has to be processed in a plant. Has to, almost always has to, because especially the thin seams, you're usually cutting a bit of rock out of there too. And you get 70% recovery off of that, but the contour mine coal is salt raw. You just right on train. So you'll have to state your, designed highwall miner web and barrier sizing, and that'll be based on a miner head width of 11.5 feet. And yeah, the rate of advance of the highwall miner, right, based on the panel dimensions, dictates the minimum rate of advance of the contour. So however much you max production on the highwall miner, and so however much it advances as far as pit is concerned, that's how much you have to keep open out in front, right, so that you can continue mining. So that's what's going to be the sort of the driving factor of our production rate. Site has an area that was historically deep mined, 45-foot centers, which means an extraction ratio of 69.1%. That was hatched in green. It is possible to surface mine existing deep mines. You can do that. You remove the overburden, and then you strip out the remaining pillars. So you'll have to decide if that's economical or not in this case. The existing contour bench is hatch blue, adverse properties magenta, and yeah, you'll have to consider how these features affect the geometry and sort of economics of the reserve. Maps I'll be providing for the project, a 200 scale and 500 scale PDF maps, as well as the base DWG, and then immediately I'm going to see what I need to do to get AutoCAD licenses for everyone, for those that wish to use it. It's not required. You can draw this out by hand. Use a ruler and a piece of string or something, So I want to make sure at this point that you're understanding the concepts and that sort of thing. And like I said, if you want to use the software, cool. But if not, it's not technically required. So the design tasks, you're going to have to determine the maximum bench width and the associated high wall height with that. You can use the average values for that and share that as a sketch or a hatch on the project map. You're going to need to estimate the average overburden removal for each reserve, the north and the south, right? So you have to calculate how much overburden there is, how much you have to remove, use the swell factor, right? And then see if you have enough space pre-existing to accommodate that. If you do not, then a fill, will be required, right? So you have to assess whether a side hill or valley fill is required, and also, tell me what that volume is and identify the chosen location for it. You have to lay out the location and grade of access or haul roads to serve the operation. Obviously, on the bench itself, it's going to be pretty flat, but we'll look at some more information here in a minute, and I'll show you on the map how you may want to approach that. Provide a blasting design, and so this will be for the North Reserve for average conditions, right? So average overburden thickness that you're going to be mining, and in the case where it's previously stripped, that'll range from like 40 feet to something larger, right? So if that average, and calculate the burden spacing, stemming, tell me the hole depth and powder factor. So based on that average bench height, and assuming drilling within 4 feet of the coal seam, and this will all be based on the Anderson equation. Unless you want to use another equation, you can, but I would suggest that. Then select equipment. So you'll have to specify the size of the shovel or excavator and the number of haul trucks to remove the overburden. And you'll need to support that choice with the cycle time calculations and production estimates based on your chosen haul distance and the road grade. Like I said, on grade it's going to be pretty flat, depending on where you're storing your excess material until you can get started using the haulback method. Like how far is that? So how many trucks are you going to need? Well, you would also need front-end loaders and trucks to haul the coal out. But in this case, we're just going to skip that at the moment. That's the same calculation as you would do for the truck shovel, right? It's the same calculation. And where, we don't know where we're hauling this to, I could determine just a place on the map or what, here's your plant. But we'll just do the one for now and just know that, you would also be doing this for the truck shovel stuff. Also keep in mind that you're going to have at least one dozer, because you're going to be, building roads and that sort of thing. And, obviously cleaning off areas of the high wall, prepare for blasting and clear back vegetation. So you'll actually probably have more than one, but we're just going to keep it at this for now. Because we're also going to be laying out high wall monitor panels, and these have to meet the ARMS high wall monitor design criteria, and for both in the north and the south, right? You may need more panel change-ups, depending on how that depth of cover changes, but at least one for the north and the south, and then you'll need a monthly production forecast, so in clean tons. So use a high wall monitor advance rate. You have 4 holes a day. You have your entry spacing, your seam height. You can, calculate how much coal you're going to recover, and assume 70% recovery at the plant. Although the contour coal, strip coal is sold raw, and then also, report the total for the, entire mine. How much your production is for the whole mine, and yes. I repeated this again, so that there's a little bit of repetitiveness in here, but it's kind of more of a reminder, that the strip production is going to be based on that minimum contour advance to stay ahead. Estimate how long it will take to mine the entire property, so like mine duration. How long is it going to take to mine this? If it was me, there's more than one way to do this. You can use the total mineable length and your daily or monthly, high wall miner advance rate. Or you could use the contour advance rate, right? Because for this project, theoretically, these advance rates would be the same. And that way you're always staying out just enough ahead. You have just enough exposed high wall, right? You're minimizing disturbed area, minimizing your sediment problems, minimizing how much high wall you have exposed, minimizing exposure to people from a safety perspective. So theoretically, you're only going to open up that much at a time because it's as fast as you can mine. If you design the contour based on the high wall miner, theoretically you'll never be behind. However, in practice, this is more difficult than it sounds. It's more difficult to keep the strip advanced out ahead. And there's a number of reasons for that. One is just high wall miner rate of advance is just fast, right? It's fast. 2, it also depends on hole length, right? Like I told you, we're going to use an average for this property that we've just assumed. But if you only had 500-foot holes, then you're going to obviously mine more of those than if you had 1,000-foot holes, right? So, it's especially when you start getting around towards like points and things like that, where your holes are shortening up, you're getting ready to make a turn, you catch up faster than you think. But we will use the theoretical sort of best for this case. And then finally, you're going to design a sediment pond for the runoff into Isaac's Run. So not necessarily the runoff into other tributaries, but into the main Isaac's Run right here on the map, this area. So we're going to put sediment control in here somewhere. You'll have to figure out the drainage that's coming into here. Because you'll also have like diversion ditches, right? So, like for example, in this area, you'll have diversion ditches up to here to keep water, from just going straight over the hillside and then divert them into the sediment pond. The same can work up here as well. You could also put a second sediment pond here and do different sort of ditch layouts, or you could even put in a sediment ditch, right? So a large ditch with embankment space throughout it to catch the sediment. It's probably less practical for this. I've seen them used before, but generally speaking, the steeper the topography, the less the harder they are to put in. Okay, so I've seen them, but they were kind of down on like this level, and we were mining on multiple seams above. So for this, I probably wouldn't use a sediment ditch, and instead would do what I'm telling you to do, and that is put a pond somewhere up in here where it starts to flatten out, right? And then you'll divert water to that. There. Okay. So back to this. Design a sediment pond. So what you're going to actually submit, I didn't realize this split between 2 pages, but whatever. An engineering project report in Word format for each section. You'll want to include, sort of the objective or scope, or at least a subject, right? So basically an introduction to that section in just a few sentences, really, just to say this is what we're talking about. And then you'll need to provide all of the methods and assumptions that you used. It's any equations, what inputs you used for what. So for the high wall miner, for example, you can just say, overburden depth was this, seam thickness was this, and these were my results. You can also just take the ARMS high wall miner result page and just screen capture those results and as a figure in your report, right? So you can just say, this is what all I put in. Here's the input screen. Here's the output screen. This is what we got out. It meets the criteria. That sort of thing. Full-size maps, those don't embed well into like text, so those can be just attached at the end. And then I do provide a sort of an example report outline. It basically just takes every section that we just talked about, right, and kind of in order, puts them together. I'll also provide you guys with some other examples of engineering reports and that sort of thing to get an idea about all of that. So for what to do when, part 1, remember I said was going to be pushed back. I'm going to make part 1 of the project due on November 2nd. That's 3 weeks after the midterm week. And it will be section C through H. So just introduction and description, bench geometry, overburden removal and placement, fill requirement, like do we need a valley fill? So I'll still have to do some additional instruction on this. Same for haul roads, which I'm about to do right now. And then we've gone through blasting as well. So we've already covered almost all of this to get up to this point. And even beyond that, we've talked about some stuff already. So, but we're going to do even more of that as we go along. And right now, what I want to talk about is the DEP Technical Handbook. I posted this on the website and told you a number of chapters to check out in here that they pertain to the project and surface mining in general. I'll also point out that this does include surface areas of underground mines as well. Okay, so the drainage structures and all of the surface reclamation stuff that gets discussed in here, also applies for that. Chapter 1 is pre-planning and sediment control, and it kind of just talks about what to think about before jumping straight in. Chapter 2 is estimating runoff. We're going to skip that for now, but that is important in sediment structure sizing and things that have spillways and things like that have to be designed for a certain period rainfall event, be that 5 or 10, or maybe even 25, depending on the case. But we're going to skip that for now, and then we'll talk a little bit about sediment dams here, the valley fill. We're talking about the valley fill and the side hill fill. And yeah, so we'll start with chapter 1 though. And the big things in here. So sediment control, a lot of factors influence erosion rates. Okay, and that's everything from the type of soil to the amount of rain, right? The slope. There's a lot of things going on here. But through a lot of research, the U.S. Forest Service, Soil Conservation Service, determined that, that sediment storage should be a minimum of 0.125 acre feet, which is a dimension of volume, right? Imagine an acre of water that's a foot deep per acre of disturbed area. And so what that does is, let's say, for example, you have 100 acres of disturbed land. You would need to have sediment structures that were 12.5 acre feet in volume, right? And so an acre foot, I guess we'd say, an acre is 43,560 square feet, right? And then you have another dimension of a foot deep. That means that an acre foot is 43,560 cubic feet. And from there, you can then calculate, what dimensions your sediment pond needs to be. Back to we need to let's go to valley fills in chapter 8. Oh, there we go. This talks a lot about, the purpose of these, and, just to get rid of excess spoil and have a place to store it. Valley fills should be looking at the most moderate slopes, naturally stable areas available. Sure. They should be. It gives you all kinds of different considerations: slope at the top of the fill, base width, channel. You need to do a geotechnical investigation, minimum design requirements. Fill will have a long-term static safety factor of 1.5. Now that's going to be a slope stability calculation. We haven't gotten into that yet, but we will sort of jump into it a little bit. Then it's got things for outer slopes and rock cores. You have to have a durable rock core within the fill. And this talks about all the plans and designs. So when you submit a plan, you'd have to have a profile view of the valley fill showing the original ground. They'll also, require a plan view, cross section of the core, different cross sections either through the bench, so you can show the dimensions of all that. Yeah, foundation preparation, keyways, and things like that. Like you would, what did you do to the bottom of the fill area prior to putting the fill in to ensure that it stays stable. And then certification. The fill shall be designed using recognized professional standards and certified by an approved registered professional engineer. So this is one of the things. And not everything has to be certified. This is one of the things that does have to be certified. Sediment control structures. Storage volume, once again, 0.125 acre feet per area of the proposed disturbance of the valley fill and proposed mining operation above the fill. So if you are putting in a fill, that counts as part of the disturbed land, which makes sense. It's disturbed. Side hill fills are a little bit different. Okay, there's still a way of, making a stable fill, so not an outslope kind of thing. When I say outslope, just imagine like backfilling a high wall, but you have excess spoil, right? And then it just goes over the hillside. Those aren't stable. I've seen them happen unintentionally. We just ended up having way more rock than I guess we thought we were going to, and had the space to store it. But yeah, you end up with a less stable fill. You end up completely covering the bench, right? So you got to build a road back in to access, because you're still mining, right? You're still mining out ahead. But now this whole thing's filled back in. There's rock over the hillside, and you've got to come in from a lower elevation and then start going back up to get back up to the pit. And it was it's a major pain. With the amount of material we have now and trying to do an approximate original contour. Pre-law, if you were just going to shoot it off and throw it over the hillside, then yeah, it's out of the way, sure. But in modern times, that just does not work well. And a side hill fill would be a better option because it allows material to be placed right, and you can above like a natural terrace or a bench, and then so that helps prevent movement. One of the reasons for using a side hill fill instead of a valley fill is if, for whatever reason, your post-mining land use needed to utilize more rolling terrain. So this is going to make the topography more rolling than it was previously, right? Not as steep. So it depends on your post-mining land use. This actually could be a good idea. And then finally, there's durable rock fills. This is basically the same as a valley fill, but if it has at least 80% durable hard rock, so we are talking about rocks that do not slake in water, and what that means is the slake durability test, right? So they have a slake durability test. You basically put a sample of the rock in water, it rotates in a screen through water and just keeps going, and then you measure the starting and final weights to see how much is slaked off or how much the water has caused the rock to lose its mass. So for durable rock fills, it needs to be sandstone, limestone, sandy shale probably. And if you have that, then you could do a durable rock fill, and the requirements are a little bit different than valley fill, but the concept is the same. So there's our fills. Haulage and access roads, chapter 13. Let's go talk about that. There we go. Haulage and access roads. The biggest takeaway from here, the overall grade shall not exceed 10%. So you can have more than that. You can have a maximum of 15% for 300 feet in 1,000 foot of road. So for 300 feet per 1,000 feet, you can have 15% grade. But it's got to be, like I said, overall does not exceed 10. It talks about different styles of road, the grading, sections that have embankments, how to do curves. If you have cut slopes, right? So like you actually had to shoot out for the road. If you have cut slopes, there's direction on, what slope angle those can be. Also talks about ditches, like diversion ditches and ditches for the road, and how often your culverts have to be spaced, right? Additional information, culvert design criteria, sediment control still has to exist. And you have to put in temporary controls during construction till you can put the permanent controls in. And that's about it for roads. So the biggest takeaway is 10% grade average. So if we come over here and we look at our mine map, where might we be able to put a road in? And if you look, there's an existing road here, but there's a little bit of a problem. And that problem is it's too steep. When it gets to here, it starts going uphill. This gets into like 20% territory. So what we would have to do if we want to start a road here is actually come down somewhere about right here. And then, we would start. This is very rough. Okay, this is extremely rough. But this is to get an idea of what to do. But we're just going to start working our way up, right? And like I said, this is real rough. But it would look something like this, right? By the time we got our road in, it would look something like this. And so let's see what the slope of this road is. We know that this is 1,420 feet of elevation, right? So this is probably about 1,410 feet. Let's get our calculator up. 1,410. And then we would subtract our starting elevation. See what that is. Type in properties. The elevation is associated with that line, so 1160. We'll subtract that. So our rise, how far we go up, is 250 feet. And the length of our road is 4,700 feet long. Okay. So we'll divide that by 4,700. And we get a 5.3% average slope. Okay, cool. That meets the criteria just fine. That's one way to do it. It's a pretty long road, but it gets to where I would probably access the reserve at, or over here. But let's look at this for a minute. So you can also come up to this point. You'll have to put in roads, along, or you'll have to fix the roads to get over through here, right, on the bench. But you could put in the new road just up to here. However, let's see here. We need to get up here to that 1,420 foot elevation, right? We got to get up there, 1,420. And then our road's going to be over here somewhere. Once again, it's 1160, but we're probably maybe like 1150 here, because it was 1140. So let's say 1145. And so our rise is 275 feet. So 10% grade, 275 feet is 2,750 feet of road, right? But let's just see here. Oh. 2,750. Oh. That means that the grade's going to be too steep, right? So you'd have to do it. You can do it, but I'd probably actually start maybe over here somewhere. You have to cross the creek again no matter what. So I'd actually probably start maybe like right here and just bring my road in up this way. And then I'm going to start, I'll make a turn across the creek and then start coming over this way, climbing up somewhere, maybe here, maybe not. We'll try it. Let's just try it. We'll put our turn in and then see if we can get up there somehow. Let's see if this works. List 26. Oh, it's not quite long enough. Oh, but I think you get the idea that you would have to from this way. You're gonna have to put in a switchback, probably two, right? unless you come further out this way. You could just road out through here and then just switch back and come back up to here, or do it the other way. Maybe that's better. I don't know. Come up around this side and switch back around. Either way, it is doable. For this project, I just want a close estimate, right? Just show that you know the concept and how to do it. If we had Carlson software or other mining software, especially you start using surfaces, for the topography and that sort of thing, and you can just lay out a road on grade through their commands, and it'll just put the road right on grade for you. That's nice, but you need to know in your head how this actually works, because I don't know. One day you're going to be standing outside in the field, and somebody's going to be like, "Man, we need a road," So yeah, we need to know that. Okay, so we put our road in. Like I said, you can also access the property here. This is too steep, so if you wanted to come up and start up in here somewhere, you're going to have to, like I said, start down here somewhere and put in switchbacks and stuff like that. So that concludes our presentation for today, our introduction to the project, the actual narrative itself with all the information you need to complete it. Let's see, we talked about haul roads. We still need to talk about fill. We talked about fill and the requirements, but we need to do an example on that for volume calculations and that sort of thing. So we'll do that next time, and with this, we'll see you then.